Thank you, Rainer. So, as you already said, I am presenting the work of Studio Marjan Colletti from the University of Innsbruck, the Institute for Experimental Architecture. As Rainer already said, Marjan has been a professor there since 2011, 1 year now. I have been there only, this is my second semester there, so I will try to do my best to present the work that has been done there and the research that we're currently working on. This is the image from the exhibition. As you said, we presented a lot of videos and images and I think no models actually. So a short statement of the interest that we pursue in the studio, which says that we believe that there is a desire and need for better material properties, higher sustainability, and possibly also embedded technology. Here are some images from the first studio that Marjan Colletti was leading in Innsbruck. These are from 2007. Then it was called, the topic was Cyber Baroque. So after that, from 2011, we have made 3 studios under the topic Biotronic Gardens, which started with a design project for creating biotopes for species, and for the first year studio, design studio, for creating pneumatic prototypes of architecture that could breathe, move, sense, react. Could you show the first video? This one? So here you see some of the prototypes that were designed, built, fabricated and programmed by first year students. This is a video from the final installation. Unfortunately, this was done 1 year ago, but almost none of the projects have survived that we could have brought in here. So the students started out with some organisms from nature. They analyzed it and created architectural prototypes according to these principles. Some of them are very simple and well, most of them are pretty simple. So since the last semester, we have a brand new robotic laboratory in the university, which we have been trying to integrate into the design studios during the last 2 semesters. But this is the setup that we have at the moment. It's pretty unique. It consists of 3 ABB RAB 2600 robots, each with 20 kilo payload and multi-move setup, which means that they can work together in a coordinated way. And we use custom end effectors tools that we build by ourselves, and the software that is well known and natural for architects, for the students like Rhino, Grasshopper, HAL. Can you show the second video, please? So there's basically how it works. There is a setup. The students only have to learn a few simple new tools, and and the code and the programming for the robots is generated automatically and in a very intuitive way for the students. There is also we can also control them manually, and here you see some of the tools that the students have built. So very simple things, but the strategy that we try to pursue is that in order to design a new fabrication process, you need to start with a new material to figure out the tools that you need to use to control this material. That's why we haven't used any pre-set up robotic ready-made tools that much. So our current research follows the title robotic foaming. We started out with some keywords of characteristics that we wanted to create. We started thinking about filamentous, fibrous, porosity, soft light, and how to create something like this. And during the process of experimentation, we actually discovered that the prototypes that we created with foam, you always see the foam prototypes on the left side, and some analogies from the nature from the right side actually have incredible material self-organizational principles that were very interesting and inspirational for us as architects. So here you see a cross-section of a bone or a sequoia trunk compared to one of our tests, mangrove roots and the batwing tissue. So the material that we use we used for these experiments is a self-made mixture consisting of polyurethane foam, hardener, water, cement, plaster, also color pigments, fibers. And the reason we ended up with this was the main reasons that it created this aesthetics that we were thriving, and was also readily available. We could get it easily, and it was also relatively cheap. So from these standard components, we manually mix together the material, and once it starts to get harder, at one point it reaches the state of where it becomes very viscous, where you can stretch the material a lot, and it starts to form fibers. At this point, then we attach it to the robots. And to set up the tests, we also made a lot of manual experiments before to test the structural properties or color or the material limits, how big we can get, how long, how spatial. And then these diagrams show basically what robots are doing. So if you imagine